All right, Iman, talk to us. Not Imans. Put your phones away. Close your mouths. Listen to Iman. Okay. It turned out you didn't use it, but it doesn't hurt to know. All right. So you didn't write down your ins and outs explicitly. Maybe that's helpful for people if you didn't kind of see what's going on with the chain rule here. So first off, I like how you rewrite this so that the function squared is more clear, so that your in is obviously secant x now when you've rewritten it like that. And then your outer part is more clearly 4 times the inner part getting squared. And then if you write down the ins and outs, then hopefully it's a little bit easier to see what you need to do. Derivative of the inside, she did that right here. That's secant x tangent x. And derivative of the outside is 8 times the inside. You just do your power rule on that. And then the inside is secant x. So that would be 8 times secant x. And that's what this is. 4 times 2 secant x is 8 secant x. So she's got 8 secant x for d out times secant x tangent x. That's for d in. And then she can just multiply the 4 and the 2. They're both outside. That's 8 secant x times another secant x is secant squared x. And you have the tangent x's tacked on at the end. And they're all just kind of running together because it's all multiplicating. Multiplicating? I'll pretend that's a word. All right, so that's 55. If you have a trig function squared, I recommend you rewrite it like this so that it's a little more clear what's in and what's out. Any follow-up on 55? All right, thank you, Iman. Hi, Mohammed. Homework?
Yeah.
Cool, thanks. All right, 43, who are you? Me, all right, go, you.
So you come slope of the origin, so then you take the derivative of the function. Derivative of sine is cosine. And
Yeah, that's true.
I know I did a problem for this, but what's the problem asking?
The slope at the origin.
Okay. I plug in 0, and then use the unit circle. Cosine of 0 is 1. And then y prime 0 equals 1. That's the slope. Because m equals f prime. But in this case, we're using y prime. And then for part b, same thing, but we're going to use chain rule. And so the inside is 2x, and then the outside is sine. And then you take the derivative of the both. So the derivative of 2x is 2, and the derivative of sine is cosine, like in part a. And basically, we bring those down and multiply each other and include the inside. And this is where we plug in 0. And using the unit circle again, cosine of the
0.
Yeah, cosine of 0 is 1.
Yep.
And 2 times 1 is 2.
All right. Ta-da. And what do you think might be the slope if we had sine of 8x in there? Then what would be the slope at the origin? 8. And if it was sine of negative 13x, what would be the slope at the origin? Negative 13. So they wanted you to kind of just take these 2 data points and extrapolate. What do you think the slope is at sine of ax? Probably it's a. Prince? Yeah, sure. There you go. 59 was just another very similar to 55. This one's a little bit tougher because the inner part has its own inside part. So we have like nested chain rule. This is the first one that we're looking at with chain rule inside of a chain rule. Who was 59? All right, Raisa, talk to us. I'm just wondering what's this x here? Oh, okay. Oh, because 2 yin times d out. All right. All right. So when you do d in times d out, 2 times a half cancel, and then you have a cosine 2 theta timesing in, which is sine 2 theta. Ta-da! Now, I mentioned this at the outset with this one, there's chain rule inside a chain rule. So she wrote sine is, the inside is sine of 2 theta. That's great. What's inside of sine? 2 theta. So you can think of this, oh, this has its own like mini chain rule for getting the derivative of the inside part. Derivative of this guy's inside is 2. Derivative of sine is cosine of the 2 theta inside the trig function. So that's where the dn being 2 cosine of 2 theta comes from. I started showing this on Friday in my block 3. I'm going to start doing this more in this class. Don't hurt yourself, Prince. This Marcos will get you. Where maybe at a certain point it's helpful to not necessarily write down all the ins and outs all over the place. Like here, when you're doing the derivative of the in part, you probably don't want to write down like a mini in and a mini out for that guy. Just say, well, this guy's inside is 2 theta. The derivative of the inside of this thing is 2. Derivative of the outside is cosine, and the inner part is still 2 theta. Ahmed. Derivative of, I just did. Okay. The inner part is sine of 2 theta, right? What's this guy's inside? What's the derivative of 2 theta? 2. So that's d little n. Then what's the derivative of, well, what's the outside part for this thing? Sine. What's the derivative of sine? Cosine. So we have dn times d out, where d little n is 2 and d little out is cosine. What's inside our trig function? 2 theta. So the inner part, like the thing that's inside the trig function, is going to stay inside there. So that's still going to be a 2 theta. So that's how she got dn. She just didn't feel the need to write down explicitly the little in and little out that makes up big N. So that's going to be the same idea as for like 34 and whatever thing Prince is doing over there. Any other questions for 59? All right. 34. This is especially ugly. 3 to 34. All right, Narose. For this one, I'm going to explicitly write down ins and outs again because it's so obnoxious. That's fine if you didn't, but I find it for something like this to be helpful. So, what's big in? What's the biggest thing that's inside something? 2 plus. And what's happening to that? It's getting cubed. All right, so that if I were going to set up ins and outs, I'd say, big picture, I have this huge thing getting cubed. So that's huge thing is my in, and then in cubed is my out. Any questions with this setting up big in and big out? Now, when you come over to do d in, this is going to require its own little chain rule, right? So when you do the derivative of this part, what happens with the 2? It goes to 0, because the derivative of a constant term goes poof. And then you have to do chain rule on this guy. What's the derivative of this guy's insides? 2x. And that multiplies, so that's like derivative of little n. And then derivative of little out is what? So 4, and then that inside stuff is x squared plus 1, and it's now getting cubed. So that's the derivative of the little out. So big N is all that stuff getting cubed. When you go to do the derivative of big N, he's got his own inner and outer stuff. His derivative of the inside is 2x, and his derivative of the outside is the 4 times that inside stuff cubed. And you can put that together, and that's 8x quantity, x squared plus 1 cubed. So that's big Dn. And if you look up in Narose's work,
Pardon the interruption, John Farrar. John Farrar, you have for coverage from 210. John Farrar with 210 for coverage. Thank you.
that's all right here on the back end of her stuff. Now, if you look at out, what's the derivative of the outer part? 3 times the inside squared. And the inside is obnoxious enough, it's maybe worthwhile writing it down here. What is big N again? The fourth. So we use original N. Unless I wrote it down wrong. And then out here, it's now squared, right? So that's big D out. And you can find that here. So 3 times that big inside stuff squared. And all she does now is she takes everything that's on the very outside, this 3, this 4, and this 2x, none of those have an exponent on them, so she can multiply all those together and say 3 times 4 times 2x is 24x. And then she's got an x squared plus 1 all cubed that doesn't want to distribute. And then she's got this ugly mess, and she just turned a plus into an x. So let's put that to a plus. And she's good. All right, so that's good stuff here. And if you're like, wait, what the hell is going on in that first line? This is what's going on there with ins and outs. Questions with 34? If you're able to do 34, you're in really excellent shape because seeing all the ins and outs of that thing is kind of annoying. All right, 95, Laura, talk to us.
So find the first derivative in columns. There are two separate pieces. So you can find the derivative of the two separate pieces. And I rewrote it so that you can just find the second derivative. Then you can do that nonsense.
Yeah, so what rule do we call this nonsense?
Product rule.
Product rule, because you got a product of 2x and cosine of x squared. So this is now product rule. What was the rule we used on the first part? That's a pure chain. So it's a pure nice chain. We got an inside part, his derivative is 2x. We got an outside part, his derivative is cosine. There's an x squared inside of it. That's cool. Then we got to go to product rule. And for product rule, this is first times derivative of the second. All right, so first is 2x. Derivative of the second is 2x times negative sine of x squared. And then you've got derivative of the first is 2 times the original second was cosine of x squared.
Then you can out and get
Yep, so negative 2x and 2x makes negative 4x squared. You don't really need to pull out the 2. There's nothing really to be gained from doing that, but never hurts to factor. So that's getting your second derivative. You get your first derivative, and then you differentiate that thing to get your second derivative. Any follow-up on 95? All right, and then Prince, talk to us about your 61 here.
Okay, so basically state what's inside and what's outside. And what's inside is secant pi t minus 1. The outside is 3 bracket in bracket to the second power. And so on the inside, you have to do the chain rule. And
All right.
after that, the inside is pi t minus 1. The outside is secant. And the derivative of the inside is just pi. And the derivative of the outside is secant x and x. And so wait, this is the thing I'm like mixed up on. Is the derivative of the outside is that how many
So you're right that it's secant tangent. What's inside the secant and the tangent?
is it in
It's the inside stuff. So instead of secant x tangent x, it's secant in tangent in. Unfortunately, because that's considerably more messy looking. So we'll have secant of the inner stuff, which is pi t minus 1. and tangent of that pi t minus 1.
And so you multiply them together, and below that is the derivative inside, but that's wrong. It should be pi. Derivative inside should be pi times secant. Yeah, you can write it.
Oh, so this, gotcha. All right.
So it would,
This is why I don't like running mini in, mini out. It gets very confusing with all the like competing ins and outs. So you've got your big in and big out. Big out is cool. 6 times the inside. Big in is annoying because he's got to do his own chain rule. You do that here. And then you put this together to create the derivative of big in. Yeah. So d in, this guy's derivative is pi times this stuff, secant of pi t minus 1 and tangent of pi t minus 1. And d out is 6 times the inside stuff, where this is the inside stuff. So we have 6 times secant of pi t minus 1. So you can put that all together, and you have a 6 and a pi all on the outside of your trig function. So you got 6 times pi. And then you have a secant pi t minus 1. And another secant pi t minus 1 over here. So when you multiply secant times secant of the same stuff, what do you get? Secant squared of pi t minus 1. And you have a tangent of pi t minus 1. So it's another chain within a chain situation. Trig functions do that a lot, unfortunately. Yeah, you did a pretty good job. You just messed up one little detail, but that one little detail made a lot of ugliness. Not that it was ever going to look great to begin with. Like, even if this is correct, it still looks like, ugh. But good stuff. Akshay, homework? Thanks. Any follow-up on 61? Good news, you have a quiz this week, and it's on, hopefully, Thursday. It'll be from everything we've done from Chapter 2, with a little more emphasis on product, quotient, chain rule. You still got to know your limit definition of the derivative. You got to use it exactly one time. So don't forget that. And also, like, hey, what's the equation of the tangent line to the curve at a point? All that stuff that we've been doing along. So it's not just going to be, here's a function, get the derivative like 18 times. It's going to be like 4 or 5 of those, and then using the derivative in different ways. I have like 1K problem, so I'm just going to leave that up there. Take notes on it. Dice. You got 1, 1, and 1. You guys, hand it in. Oh, thank you. Yes.
Has a student ever cried that like their vocal picked the most?
Has a student ever cried over what?
Like if they're like vocal picked the most, and they didn't do the homework.
I've never had a student cry for that reason, no. I don't. I had a student cry my first year. Did I tell you about that? The guy who cried because he got a text message about his uncle dying, like while he was in class.
No, I know more about
Yeah.
like.
So that wasn't like not my fault.
Have you ever made a student cry?
Not that I can remember.
Did you have a when you were in his class?
No, but my little brother had my older brother.
I cried in geometry once. I cried in geometry. I like sat there sobbing has made so many people cry.
Okay.
That's my cat. It's so dumb as a hard one.
Oh, that's a little harsh. Before you say something like that.
Don't care. You can hear me. I don't care.
Yeah, but still, shut the door. And I'm recording. Like,
What's he gonna do?
Watch your videos. Is he gonna watch your videos?
I hope not. would you please shut the door as long as we're running down other teachers? Like,
I mean,
I'm fine with whatever you
I don't appreciate you guys doing that. All right. So today we're just going to continue working through a few examples. Maybe the examples we look at today would have been helpful before you did this homework, and stuff like 59 and 95. Oops. And we've only got like a few more examples to work through. So you'll have homework tonight with chain rule. You have homework tomorrow night with chain rule. Wednesday will be a let's tie things together, do some whiteboard practice, and then Thursday is going to be your quiz on all this stuff. I'll got another notebook. So I think we finished off with example 9 on Friday. Yeah, so we'll start with example 10. Real quick, get the derivative of sine of 2x, go. Then get the derivative of cosine of x minus 1. Again, get the derivative of tangent of 3x. And it's a race. Can you differentiate all 3 of those before I put up the next slate of example problems? Probably you can.
on the Jagger,
Yes, sir.
is B like this supposed to be a Y on it?
What?
Is this supposed to be a B? Not is there supposed to be a Y equaling the
Oh, 11B. I was looking at the wrong B. Yeah, it probably should be. Oops. It's your third bullet point of the day, Prince. You're racking them up.
Wait, is that possible? Like take the derivative of something that's not equal to like
Yeah, you just differentiate an expression. That's fine. And then that would be like a d over dx and around that sort of situation. What? Yeah, if you're done examples 10, then keep going to example 11.
is that cosine to the third power?
Why did I put example 3? 10, 11, 3. Man, that's like my son's kind of counting. Actually, you can count that from there. Don't think he's an idiot. He's just 3 years old.
Is that cosine to the third power?
Yeah, that's cosine where?
The example 11.
No, that's cosine of 3 times x squared. So the cosine of 3 there is your coefficient. The x squared is getting multiplied by the cosine of 3, which is just going to be like a number. right, let's go over these things. For number A in example 10, what's the inner part? What's the derivative of 2x? 2. So d in is 2. What's the outer part? What's the derivative of sine? What's inside our cosine function? So when you have chain rule, whatever's inside the original outside part is inside your derivative of the outside part. So if the outside is a cosine function, then the stuff inside the derivative of cosine remains the same as the original inside stuff. So if you see, hey, I've got a 2x inside my sine function, there will be a 2x inside the sine's derivative. Ta-da! You don't necessarily have to write down ins and outs all the time. And some of you were discovering that on the homework. Man, writing all these ins and outs, it's really tedious. Can I do it without that? Yeah, probably. Sometimes the ins and outs is really helpful. See example 12. But sometimes the ins and outs just kind of becomes a crutch, and it's useful for learning chain rule, but you don't necessarily want to do it every single time if your ins and outs are relatively simple. Any questions with example 10a? How'd you do? All right. B, who's your inside? What's that thing's derivative? 1. Hardly even need to write it. And what's the derivative of cosine? Negative sine. What's inside your sine function? X minus 1. What's 1 times negative 1? Negative 1. Ta-da! How'd we do? Hey! Tangent function. Tangent of 3x. Who's inside? What's his derivative? 3. What's outside? What's the derivative of tangent? Hey, knowing your trig stuff is cool. So secant squared, what's inside your secant squared function? 3x. So you got 3 times secant squared of 3x. Done. How'd we do? Any questions with examples 10, A, B, C? All right, example 11, things get moderately more difficult, but not nearly as hard as some of the stuff you saw in the homework. What's the derivative of cosine of 3x squared? What's the derivative of the inside part? 6x. What's the derivative of the outside part? What's inside your negative sine? 3x squared. Now this you can clean up a little bit and say, hey, 6x times negative sine is negative 6x, and then sine of 3x squared. That makes it look a little bit better. Because otherwise it's easy to turn like that multiplication of 6x and negative sine into accidental subtraction, which you don't want to do. I'm missing a final parentheses, aren't I? Is that the issue? Sorry. It's bad aesthetics. All right, in number B there, this is where things can get a little confusing. Do we need chain rule at all? Well, what's actually inside cosine? 3. What's the x squared doing? It's multiplying. What is cosine of 3? Like very generally speaking, what is cosine of 3? Like a decimal. Like it's a number, right? Do you know what cosine of 3 is exactly? No. It's kind of like pi or e or 7. It's just a number. So this is just a coefficient that's multiplying x squared. If this were 5x squared, you would differentiate it exactly the same way. What's the derivative of 5x squared? 10x. So what's the derivative of cosine of 3 times 2x, times x squared? 2 cosine of 3 times x to the first. Because this isn't cosine of 3 plus x squared, just like this isn't 5 plus x squared. This is a coefficient times an x thing. So you do your power rule, multiply the exponent down in front to the coefficient. Now your coefficient is 2 cosines of 3, and then you reduce the exponent by 1. Fine.
We chain rule on cosine 3. We could chain rule on, like, isn't it 0?
And then I guess you're doing product rule also. But does cosine have any x in it? So you don't need to worry about it. Like if you want to do this with product rule and say, my first function is cosine of 3, So his derivative is 0. And my second function is x squared. And say derivative of the first guy times the second is 0, because the derivative of the numbers is 0. Plus, original first guy is cosine of 3 times derivative of the second guy is 2x. You end up in the same place. But that was a lot more work. Ryan?
Why can't it be written as 2x cosine 3?
You could write this as 2x times cosine of 3. And maybe that looks a little better to your sense of beauty. I don't know. But yeah, that would also be totally fine. Or you could write x times 2 cosine 3. Just don't put the 2 or the x inside the cosine function. C. I find it helpful to rewrite this when I have a trig function squared as the trig function of whatever's inside it, all raised to that power. And then that makes it a little more clear what's in, what's out. So what's the derivative of this guy's inside part? Negative sine of x. And then what's the derivative of the outer part? Times 2 times the inside, which is 2 times cosine of x to the first, which you don't need to write the exponent. And then if you want to leave it like this, sure, it looks a little weird, but that's fine. If you want to rearrange the factors, say this is negative 2 on the outside of all my trig functions, and then I have a sine of x and a cosine of x. And that's cool. I think if you wanted to use a trig identity, there's a trig identity for that, but it's not one of your normal ones, like at all. I think that's like a double angle identity, so you could turn this into like negative sine of 2x. If you see that on like a test, kudos to you. If you don't, this is totally fine. You don't need to turn that into negative sine of 2x. C and D are actually real similar. How should we rewrite D? Cosine of x all to the 1/2, and then it's basically the same idea that we just did, but with a different exponent. So what's the derivative of the inner part? Negative sine of x. And then that multiplies to the derivative of the outer part, which is 1/2 cosine x to the negative 1/2. And then here we can clean this up a little bit. What's going to go in the numerator of our final expression? So the numerator, negative sine of x. What's in the denominator? 2 cosine x to the 1/2. Or if you wanted to call that 2 square root cosine x on the bottom, that's fine too. So the numerator is like negative sine x times a 1. That's negative sine x. The denominator, you have a 2 down there already. Throw cosine down there as well to make the exponent on the cosine x positive, and you're good. So examples 10 and 11. Any comments?
Could you repeat this for example 11?
Example 11, part C. So at the beginning, rewriting it so it's more clear what's in and what's out. And then the derivative of the inside is negative sine x. And then the derivative of the outside is 2 times the inside to the first. Okay? Laura?
Would I have to rewrite the line that
No, you can leave it like this. Awkward is okay. There's nothing like morally wrong with awkward. Whoops. Last thing we're going to get to today, we're not going to get to 13. Oh, darn. We'll have time tomorrow. That's fine. So this thing is now like layered chain rules. And you saw this a little bit on the homework. So you have sine of 4t squared minus 1, and then all of that is cubed. So this is where writing down ins and outs is maybe helpful again. So you have this big inner part that is sine of 4t squared minus 1, right? And then that whole inner part is getting cubed. And then writing that down like this, starting from turning the sine cubed into sine of this whole thing cubed, then you can kind of go from there and say, oh, for doing derivative of the inside, I'm doing the same thing that I did over there, And then derivative of the out is just 3 times the inside squared. So let's do that part first. 3 times the inside squared. That's not terrible. And then the derivative of the inside, what's the derivative of this guy's inside? 8t. And then derivative of sine is cosine, and what's inside your cosine function? 4t squared minus 1. So that's d in. This big ugly thing is d out. And remember, in isn't really just in, it's that sine function with 4t squared minus 1 inside of it. So you then take these two things together to multiply, and we've got the 24t on the outside. Because you have 3 times 8t. Say again? It's right there. So that just stays inside. So you got your homework tonight. See you tomorrow.